Welcome, everybody, to the second session of the Richard Askey Day. Our first talk today is by Warren Johnson, Connecticut College, Notes on the Lagrange Inversion Formula.
Thank you, Dennis. I'd like to thank the organizers very much for putting this together and for the honor of speaking in it. I want to talk about, so I've changed the title slightly. I want to talk about an old project of mine that Dick was interested in and that has lain dormant for a while, and this is a great excuse to get back to it. Some years ago, I was collecting old proofs of Lagrange's theorem for expanding a certain kind of implicit function in a power series. I want to start with an identity I discovered 20 years ago this month, a very peculiar generalization of Leibniz's rule for the nth derivative of a product with this function phi stuck in here in this nonlinear way. Notice that the sum is symmetric in U and V, even though that's not obvious from the sum. It's obvious from the evaluation, as long as you believe the evaluation. You might therefore be tempted to look at the more symmetric looking sum, where instead of this being a V prime and having one less derivative, you have a V and the indicated number of derivatives. You might hope that this would be at least as nice. It turns out that it's not, but in order to prove P1, all you actually need is for this second sum here to be a function of u times v, and I'll show you that in a little bit. So in fact, the function of u times v that it turns out to be is this, so it's not greatest function of u times v that you'll ever see, but it is a function of u times v. So I sent these to Dick, as one did, and asked him if he had seen them before, and he hadn't. Could they really be new? Surely not. I think a few of you have probably heard this story before, but even the rest of you can probably guess that they're not new. 2 months later, I found them in a paper by Pfaff from 1795. Even Pfaff's proof is largely the same as the one that I had devised, although his notation is somewhat different. A month after that, I saw the first one, the more interesting one of the two, P1, in a paper by Cauchy from 1826, as well as a symmetric variant of it. So there is a symmetric sum rather than getting rid of the v, rather than making the v prime of v here and making this an n minus k. What you want to do is do the same thing on the other side, and then you get a nice symmetric sum. I mean, if you're a historian, I think this is great. If you're a mathematician, it's a little bit disappointing. Dick, however, encouraged me to keep working with these things, even so, and so I did. Let me sketch how one might go about proving them, how I prove them anyway. Let me set capital phi to be equal to the right side of the second one, the more complicated one of the two. And let me set capital Fn of phi, u, and v to be equal to the right side of the first one. If you subtract phi n, or Fn from phi n, you wind up getting a sum that looks like this, and since n has gone down to n minus 1 here, this is now a phi. This is a phi, this is a capital phi with an extra factor phi prime here. And so this then gives you one connection between these capital phis and the capital F's, these two sums. You have this. Since these are binomial sums, as you might expect, you can get another connection by using the Pascal recurrence. And if you do that, you find that f sub n plus 1 is phi sub n with an extra factor of phi and a v prime, plus this sum. Now this sum, you'd really rather have one more derivative here and one less derivative here, but fortunately we know how to do that. That's the product rule. If you work out what the other two pieces of that product rule are, one of them is an f, or is a derivative of an f, and one of them is a capital phi. And so that then gives you this relationship between the f's and the phi's. That capital F sub n plus 1 is these two phi sub n's plus a derivative of an f sub n. Now remember that I said all I needed to prove P1 was for this capital phi to be a function of u times v. We see that here, because here I have u in this slot and phi v prime in this slot, and here I have u phi in this slot and v prime in this slot. And so if this thing is a function of u times v, then these two things cancel each other, they're the same. So therefore what? Once those are gone, all you have left is this, and you've got an extra derivative and you've got extra phi, and that's exactly what you want. And so P1 holds for n plus 1 if it holds for n. And then once you know that, then this other relationship that we have between the f's and the phi's allows you to figure out what this phi has to be. And this is actually the way that I proved this originally. I didn't know what the phi was going to be. I just needed it to be a function u times v, and it turned out, fortunately, that it was. All right, to get the Cauchy one, it's a consequence of P1 alone. You don't need the P2 for it. You just change n to n minus 1, u to u phi prime, multiply by n, and manipulate the binomial coefficient a little bit. This gives you this, and you can rewrite this a little bit. Now, the identity that I'm trying to prove here is this capital C, and here I have this little c. And if you stare at this for a second, what you realize is that if you add these two things together, you've got a common factor there, and of course the binomial coefficient is common. These two things, if you put them together, complete a product rule. These two things, if you put them together, complete a product rule. If you add these two things together, you get this identity P1. So therefore, subtracting little c, which is a consequence of P1, from P1 gives you capital C, which is Cauchy's identity. Okay, so now let me explain why I wanted this. Larry, let me change u of x. I really didn't need to rename it, but for whatever reason I did. V, let me take to be this function phi that's occurring, and then just do a tiny bit of fiddling around. And we get something that I call, if you do this, you get something that I call the Lagrange lemma. This is what I wanted. This is what led me to these identities, these Pfaff-Cauchy identities, was wanting to know that this was true. And the reason why I wanted to know this was true, and the reason why I call it the Lagrange lemma. So notice I'm not using Lagrange's lemma here. I'm saying the Lagrange lemma. There's a distinction. Lagrange sketched a method of verifying the first several terms of his series, which I'll remind you about in just a little while, in his Theorie des Fonctions Analytiques of 1797. Now, this is, as you may know, a series of lectures on calculus, essentially, for the students at the École Polytechnique. And he doesn't want to do his original proof of his theorem from 1770 with this audience. And so what he does, but he wants the result. He wants to mention the result, but he doesn't want to do his original proof. So what he does instead is he sketches a method of verifying the first several terms in the series. And I asked myself when I was reading this some 20 years ago, what would I need to know? What would I need to know if I wanted to make that argument into a proof? And the answer is, it's exactly that lemma, the Lagrange lemma on the previous slide. All right, so what is Lagrange's problem? Lagrange takes a variable z to depend on two other variables, x and a, by this odd-looking equation with this function capital phi in it. Given this equation, what Lagrange wants to do is to expand some other function f of z in powers of x. And since z depends on x and a, if we expand in powers of x, the coefficients will be functions of a. Okay, and it's easy to work out a few of them. Since z equals a when x equals 0, a0 of a has to be f of a. And we can also, once we know that, if we subtract f of a from both sides and divide by x, we have this. We can use the equation, the relation between the variables, to rewrite this like this. Then we just take the limit as z goes to a, which makes x go to 0. And a1 of a, therefore, has to be f of a times f prime of a times phi of a. The next thing that happens is we need to do, and this is the only proof actually of Lagrange's theorem that I know where you have to do this special case first, or at least where you gain an advantage from doing it first. So let's look at the case f of z equals z specifically, and let me call the coefficients in that case these var phis, phi sub k of a. And from what we've already done, we know that the phi0 is a and phi1 of a is this other phi of a. You can calculate the partial derivatives of z with respect to a and x from this equation, and that gives you these. And you notice that this one is phi of z times this one. And this is a very important relation. This is also fundamental in Laplace's derivation of Lagrange's series, which I'll get to in a little while. What Lagrange does with it is he takes the phi of z and he uses the equation relating z to x and a to rewrite it. He rewrites it like this. Okay, now let's think for a second. We've got an assumed series for z. The first term of that series is a. So we've got a series for z minus a. If we've got a series for z minus a, then we've got a series for the partial of z with respect to a, and we've got a series for the partial of z with respect to x. So just plug all of those into this and equate coefficients, and we get this recurrence that these phi sub k's have to satisfy. It's a little bit of a funny recurrence in that phi sub n occurs on this side too, and so let's subtract it from this. That's a minor complication, unfortunately, in the proof. Let's just subtract it from both sides so we have a recurrence that doesn't have that problem. And Lagrange, don't remember if he actually writes down this recurrence, but he's certainly doing this thing. He knows this recurrence, and he's using it to work out a few of these phis. And after he's worked out a few of them, he says, well, it looks like they're this. He knows this already because he's proved this by a different method in 1770, but he doesn't want to repeat that proof here. And he leaves it at that, but with this Lagrange lemma, it's actually not difficult to prove that that's what these things are. If I just assume that this is true for k less than n and insert it in this recurrence here, then I get this. This isn't quite what the Lagrange lemma gives you because the k equals n term is missing. But if we add that back in, then the Lagrange lemma allows us to evaluate the sum on the right side. We wind up getting this. And since n is big, the reason why we had to do this for n equals 1 separately is because this would just reduce to this thing equals itself if n were 1. So we had to know that. We had to know that in advance. But since n is bigger than 1 now, this proves the formula Q. That's what these phi k's are. Knowing that, we can get the full Lagrange series. We take this same relation that Lagrange had, multiply it by f prime of z, and again, we know series for all of these. We have a series for z minus a that we now know explicitly, an assumed series for f of z, and therefore for this, and also for this. And so if we plug all of those series in and equate coefficients, we get this. And here I don't have to take out the n equals 1 or the k equals. Yeah, I don't have to take out the k equals n term here. That this is now just fine. I can just do this. Again, Lagrange maybe doesn't write this down exactly, but he knows it, and he's using this to calculate a few of these a's. And after he's calculated a few of them, he says, well, it looks like they're this. And again, he has to sort of leave it at that. But this Lagrange lemma is exactly what we need to verify that, in fact, that's exactly what these things are. If I just assume this, stick it in here, and use the Lagrange lemma, then that gives me, well, I get this sum, and I can evaluate this sum by the Lagrange lemma, and I get precisely this. And so the a sub n of a's are exactly what Lagrange thought they were going to be by this argument. Okay, so that's a proof. I won't claim that it's the nicest proof of Lagrange's series, but it's a proof. I think it's an interesting proof, and it's a somewhat natural one if you happen to know these derivative identities, of course. So this then is the full Lagrange's series, that if z depends on x and a through this equation, then f of z has this expansion. Let me mention something that is not very well known. Laplace, when he studied Lagrange's series 10 years later, actually is able to generalize this by getting another arbitrary function in here, that he can put a g of this a plus x phi of z in here and still expand the thing and get this with these g's all over the place. Some of you may be asking yourselves, why have I never seen this before? Others of you may be smelling a rat here. Jacobi, 50 years after this, observes that if we just set t equal to this quantity a plus x phi of z, then z by this equation just becomes g of t, and therefore we have the equation t equals a plus x times phi of g of t, and we also have f of z as f of g of t, and therefore this isn't really a generalization at all. We can just use the ordinary Lagrange series with the compositions f circle g and phi circle g, and this falls out. This paper of Jacobi is really quite an interesting one. It's got a very nice proof of Lagrange's theorem, which unfortunately I haven't got time for today. I believe Dennis must have been through this proof because the main idea in this proof is used again in a paper by Gessel and Stanton in 1982. Instead, let me show you Laplace's proof, which is of the derivative identity type proofs, I think is the nicest one and certainly the best known one. So the problem again is to expand some function f of z in powers of x where you have this relationship between z, a, and x. Just set u equals f of z, just to improve the notation a little bit. Again, since z equals a when x equals 0, Taylor's theorem tells us that the expansion ought to look like this, where u is, again, f of z. And so all I need to do then is prove that this nth partial derivative of u with respect to x n times, when evaluated as equals a, becomes this coefficient that we now know, this n minus first a derivative that we've seen in this other proof. How do you do that? Well, we've already noticed this relation between the two partial derivatives of z, and the partial derivatives of any function of z, such as this u, will have the same relationship because of the chain rule. Next thing we do is we look at, let h be some differentiable function of z, and we look at this partial derivative and also this one. And when we compute those partial derivatives, we get these two terms, which clearly are the same, and these two terms, which are also the same because this partial derivative is phi of z times that one, but also this partial derivative is phi of z times that one. So therefore, these two expressions are the same. And so I have this, and what this allows me to do is permute the x with the a here, that if I switch these two, I still have the same quantity. Okay, once we know this, we can prove a lemma that Laplace proves, which will get us basically where we want to go. This nth partial derivative with respect to x is the n minus first partial derivative with respect to a of this quantity. If n equals 1, this reduces to this relation partial u with respect to x is phi of z partial u with respect to a that we've seen before. If we assume it holds for n and just take another partial derivative, then this is actually pretty easy. You just pass the x derivative through the a derivatives. Use this fact that you can permute the x and the a here to get this, and then use the fact that partial of u with respect to x is phi of z times partial of u with respect to a, and now you have got one more phi and one more a derivative. So that's exactly this. That's exactly the n plus 1 case of this. Excuse me for a second, I'm getting some noise in the hallway here. Okay, so that gives us this. That gives us the Laplace lemma. So now what happens when I set z equals a? Well, the partial of u with respect to a evaluated at z equals a because it's this is just f prime of a. And therefore, when I set z equals a in this expression, I just get f prime of a times phi to the nth power of a minus the n minus first derivative, which is exactly what we want. So that's Laplace's proof. And that's really a pretty nice proof. That's a proof that you do actually see in some modern sources. And I won't do the details of this, but the same argument, this is essentially how Laplace gets his extension, although there's a little bit more to be said about that, which I'll skip. But that if we have this equation, then we still have the same relationship between the partial derivatives of z, and we can use the same argument to prove this more general thing that we would need to get Laplace's proof. Again, it's sort of silly to do that because we can just get it by Jacobi's remark, but we could. But Laplace does get this that way. Let me now show you a third proof that I doubt that any of you will have seen before. And it's based on another derivative identity, but a very strange one, one of a different type than the Pfaff-Cauchy ones. So n here is a positive integer, and j and k will be non-negative integers. And I want to have n functions, each of which has at least k derivatives. And I want to define, I'll write down an example in a moment. I want to define p of k and j of these functions to be the sum of all of the different terms that are a product of n minus j of these phis times the kth derivative of the product of the other j phis. And let me have a bit of terminology here. Let me call the factors inside the kth derivative the interior phis, the factors outside the kth derivative, the exterior phis. So this j then is the number of interior phis. J is the number of phis that are inside the derivative. So for example, each term of, so if I write down, say, p of 3 and 1 of 5 phis, that's a third derivative on one phi at a time. And so it's these five terms added together with a third derivative of one phi times the other 4 phis. Okay, and let's compute a few of these things just to get used to them. P of 0 and j, that's no derivatives. There are n choose j ways to choose the interior phis, but of course there's no, if there aren't any derivatives around, there isn't any distinction between the interior phis and the exterior phis really, so you just get this product. And this is correct even if j is 0, but otherwise, if j is 0 and k is larger than 0, then we're differentiating a constant, so these p's are 0. In fact, Prouet, when he writes this down, since he's not interested in case k equals 0, starts the sum at 1, starts the sum that we'll see in a second at 1. P11, that's one derivative on one phi at a time. That's this expression, and if you want to, it combines nicely into just the derivative of the product of all of the phis. Okay, so Prouet is not really interested in these pkj's for themselves. What he's interested in is this sum, and I got ahead of myself. Prouet actually starts the sum at 1 because he's not interested in k equals 0, but if k can be 0, then you want the sum to start at 0. And let's just compute one of these things, which we can actually compute easily with what we know. If k equals 0, then we've just computed what these things are. They're just this. The phis can come out, and now we have a simple binomial sum that equals 0 because n is larger than 0. So this sum actually equals 0. It turns out that, in fact, it equals 0 a lot of other times too. Sum is equal to 0 whenever k is less than n. So remember, k is the number of derivatives, n is the number of phis. So as long as we have not as many derivatives as we have functions, the sum is going to be 0. How do we see this? Well, let's collect together all of the terms of the sum that look like this, where I have some positive number of derivatives on each of the first m phis, and then no derivatives on the other phis with at least one, so with m less than n, with at least one undifferentiated phi. Okay, so I want to try and collect all of these terms. And they all cancel. If we believe that, then that would prove the claim, right? Because by symmetry, then all of the terms of S would cancel except those in which each phi is differentiated at least once. And if you have more phis than you have derivatives, then you can't have any terms like that. Every term has to have at least one undifferentiated phi. So if we could just prove this, if we could just prove that all of the terms of this form cancel, that would prove this claim. The only terms of the sum that can contribute a term like m are the ones where j is at least m, because all of these first m phis have to be interior phis in order to get derivatives on them. The extreme case is where they're all interior phis, where they're all inside the kth derivative. That just gives us this. And this does contribute terms like m. It contributes this multinomial coefficient k, choose a1, blah, 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 am, terms like m. If j is n minus 1, has n terms, but only the ones where the exterior function is one of the last n minus m phis can contribute a term like m. And each of them again contributes this multinomial coefficient number of terms like m. So the total contribution then from kn minus 1 is this, and you can maybe see where this is going now. Generally, if I have n minus r as the number of your phis, then their n choose r terms, but only the ones where all of the exterior functions are among the last n minus m fees can contribute. So there are n minus m choose r ways to choose those, and each of those again contributes this multinomial coefficient number of terms like m. So the total contribution from this for a generic r is this many terms like m. Remembering that the sum was alternating then, the total contribution of terms that look like m is this multinomial coefficient, which is present in all of them, times this, again, simple binomial sum. And the sum is again 0 because n is larger than m. It's a subclaim and therefore the claim. Okay, which means what? Which means that the sum, this sum s, is really kind of silly in a way, because most of the terms of s are really only there to cancel other ones. But the only term that's actually important is the last one, because the only terms that don't have any undifferentiated fees, those can only come from that last term, in which every fee is an interior fee. Terms never cancel because they all have positive signs. In particular, if k equals n, then s reduces to a single term that's n derivatives, n functions. The only way to have no undifferentiated functions is one derivative for each function. So that gives us this. So s reduces to the single term in the case when k is n. We can also do the case when k equals n plus 1. Then again, what do we need now? We need two derivatives on one fee, one derivative on all the other ones. And we get this multinomial coefficient times each of those terms. And those terms, again, combine nicely into a derivative of the product of these derivatives. This then is Prouhé's derivative identity. I actually don't remember whether he has this last part of it or not that we just did, but he certainly has the first two. That the sum equals 0 if k is less than n, it equals this if k is equal to n, and it equals this if k is n plus 1. So as a corollary of this, let's set all of the fees to be the same function. Actually, I want two corollaries of this. First corollary, let's make all of the fees the same. If I do that, then I can evaluate what these pjk's are. There's n choose j from choosing the interior functions. And so I get this expression. And therefore what? Therefore, when I plug this into this sum, I get peculiar combination of derivatives equals 0 if k is less than n, equals this expression if k equals n, and equals this if k is n plus 1. Prouhé's identity could be described as a Hurwitz-type generalization of this. In other words, there's this e to the n that's basically underlying this identity, and what Prouhé's identity is doing is taking that phi to the nth power and replacing it by n different phis, and then making the sum as symmetric as you can. And it turns out that you can do that also for these Pfaff-Cauchy derivative identities. That was the happy ending to that story, that I was able actually to get some new derivative identities rather than ones that were over 200 years old. The second corollary is basically what I want for the second corollary is I want all but one of the fees to be the same thing. It's convenient to change n to n plus 1. So I have so now n of them are phi and one of them is some other function h. And here all you need to do is make a distinction again between whether h is an interior function or whether it's an exterior function. If it's an exterior function, then you're getting this expression. If it's an interior function, then you're getting this one, and you get n choose k of these, and n choose j of these, n choose j minus 1 of these. And so the two of them together then have to equal 0, as long as k is less than n plus 1, because they changed n to n plus 1. And I can fiddle with this a little bit. I'm going to re-index the second sum. I can take the h of x out of the first sum, discard a couple of sums, or discard a couple of terms, and I get this. And we know from the first corollary that this sum, the sum on the left side here, if k is less than n, this sum is 0. Therefore, of course, the other one has to be 0 too in that case. Sum is 0 if k is less than n. K equals n, we can also evaluate it. The k equals n minus 1 of this was known earlier. I'll get to that in just a moment. When k equals n, we can actually also evaluate the sum, and it turns out to be this by the k equals n case of Prouhé's identity. And this also has a derivation of Lagrange's series at the back of it, or as an application of it if you want. And this goes back to Lexell in 1771. This is possibly the first proof after Lagrange of Lagrange's series. And where he gets it is the k equals n minus 1 case of the second corollary that we've just proved, which I'll call Lexell's lemma. And he also uses Taylor's theorem in this form. So again, we want to have this assumption z equals a plus x phi of z. If we set the w here to be minus x phi of z, then z plus w becomes a. And Taylor's theorem becomes this. So what Lexell does with this now is he says, this applies to a generic function f of z. Let's replace f of z and then multiply both sides of the resulting equation by x to the j, and that will give us this equality. What he does now, you can probably guess, is he sums this on j. So we sum this from j equals 1 to infinity, and also add this equation s, this one, add this to that sum. So that gives us f of a plus this sum equals this sum, which is the other side of s, and then this double sum here. Okay, well, this doesn't look too appealing, but let's just look first at the m equals 0 term of this single sum. That is just f of z. So let's take that out and combine all of the other sums, throw those into this double sum. Double sum now becomes the sum over all of the values j where m plus j is positive. If we set m plus j equals n, then that gives us this. And the inner sum here is 0 because of Lexell's lemma. So this whole sum here goes away, and we just get this equation, which is again Lagrange's series. Okay, so I'm just about done here. I want to bring this back to Dick for a moment. If we take the partial derivative of both sides of this with respect to x, we've already done the partial of z with respect to x, so we just use that and we get this. And this is a well-known thing that I'm sure many of you have seen. We can get this alternate form of Lagrange's series now by, in a slightly simpler form than this, by setting g of z to be f prime of z times phi of z. And that gives us this, where we now have an nth derivative here rather than n minus first derivative and this other thing on the other side. Jacobi, in his Nachlass, that was published after his death, he uses this to derive the generating function for the Jacobi polynomials, where this capital R is this square root here. There is actually a very nice proof of this, depending on how one feels about Lagrange's series, probably a better proof unless you really love Lagrange's series. Dick gave a very nice alternate proof of this, not relying on Lagrange's series, in one of his papers in 1978. Okay, so all that's left is some references here. So I'm going to stop there and just again thank the organizers. Jakob's talk was great. It brought back a lot of memories of me taking Dick's courses. I miss him so much, and it's just wonderful that we can all be together today for this. Thank you.
Questions for Warren. Okay, Warren, I have a question.
Yeah.
Jacobi wrote about the multivariable Lagrange inversion formula, and he needed the Jacobian determinant. Do you know if that's the first time the Jacobian showed up in Jacobi?
I doubt it because Jacobi was the expert on determinants in his time, and he wrote this. It's possible, I guess, that led to the short answer to your question is I don't know, but he wrote. He was very, very interested in Jacobians. There are a number of papers of his where he's making changes of variables and multiple integrals and things like that. So he's very, very interested in Jacobians. He writes a whole big paper on them. I have been meaning to look at that paper more carefully than I ever have. And so the short answer to your question is I don't know, but that's what I think.
Other questions for Warren? Okay, Warren, thank you very much.
All right, thank you.
Warren, if Jacobi actually proved multivariable Lagrange inversion, when I looked at the paper, I wasn't convinced he had a proof.
I don't know. Project that's lain dormant now for like 20 years. I've always meant to get back to it. And I will try and look into that. Thanks for that remark.